So this presentation is on quantum computing, and this is a part of Team Nine's presentation. What is quantum computing? Oh, it's a very complex topic to really talk about. However, there are a few ways that you can kind of simplify things so you can really understand what quantum computing really is. So a good way to really understand the topic is to understand what quantum physics is and the properties of quantum mechanics, being that quantum computing is something that derives from these two topics. It's good to know what they are original or initially before getting into actual quantum computing. To put it in perspective, the physics involved in any kind of quantum mechanics is pretty much based off of individual atoms and pretty much all things involving matter, which is everything, and in their states of pretty much where they are, how they exist. A good way to really compare different computers is to understand how a regular computer works, being that a regular computer only understands either what's a yes or no. A quantum computer can not only understand yes or no, but also all the options and variability that's in between them. So that's why, in a sense, it's a very important thing to understand, because being that we're just at the surface of what quantum computing really is, it can really brought out to be a huge thing in the future. Another thing to consider is normally in a regular computer, something people that we call it are, or that we already know it as, they're called bits. This pretty much the language that us normal people, understand when it turns to computers. But in quantum computing, they're no longer called bits, they're called qubits. And it's pretty much just another way to measure data, being that data in a quantum field can vary. It was a very needed new type of variable to put in there, so it'll make things easier to understand. Overall, though, I'd say that the quantum computing really is again something that derives from the physics of quantum mechanics, which is a whole nother topic in itself. But in a sense, without those type of physics, we wouldn't really have the quantum computing things that we see nowadays.
So how does quantum computing work? So quantum computing works through principles of quantum physics. So a few of these principles are superposition, interference, entanglement, and measurement. These are the four main principles behind quantum computing. So the first principle, superposition. So in classical computers, calculations can exist in two states, zeros or ones, binary. In quantum computing, qubits can exist in multiple states, and this allows quantum computers to perform multiple calculations at once. You can look at the image and see that it's a lot more complex than just the 0 or 1 compared to the classical bit. The next principle is interference. As qubits experience superposition, there's a probability of qubits collapsing, and in order to minimize the collapsing of qubits, the quantum computers work to reduce it and ensure more accurate results. The third principle, entanglement. Quantum particles are able to correspond measurements with one another. This is called entanglement. Entanglement helps quantum computers solve larger problems and calculate larger data and information. The last principle is measurement. When a quantum system is measured, it collapses into a possible state. It is probabilistic, and the outcome is not determined until the measurement is made. And superposition is the main reason why quantum computers have so much more potential compared to its classical counterpart. And quantum computers perform calculations based on the probability of an object's state before it is measured. Therefore, quantum computers have the potential to process exponentially more data than classical computers. And quantum computers, as I said before, work through the laws of quantum physics, which allow it to perform at a faster and more efficient rate. However, implementing these principles of quantum physics into computer science is very challenging, and large-scale quantum computers are still in early development. So and more challenges regarding quantum computing will be talked about next.
Challenges of quantum computing. Quantum computing is a revolutionary technology qubits, which have unique properties like superposition and entanglement, making them potentially much faster than classical bits for certain tasks. However, qubit decoherence, where they lose their quantum properties due to environmental disturbances, is a significant challenge. This requires new materials, computational techniques, and innovative quantum approaches. Quantum algorithms are also more complex than classical ones, demanding original problem-solving approaches from their developers. Here are 8 additional challenges. The first one being error correction. Dealing with errors caused by environmental interactions is a significant challenge, and reliable error correction techniques are essential. Scalability. Scaling up quantum computers to hundreds or thousands of qubits while maintaining coherence and low error rates is a major challenge. Third one is hardware development. Developing high quality quantum hardware, including qubits and control electronics, is crucial with the various qubit technologies to explore. Software development. Quantum algorithms and software tools are still in their early stages, requiring new programming languages, compilers, and optimization tools. Classical computer interfaces. Efficient methods for transferring data between classical and quantum computers are needed for practical applications. Standards and protocols. Establishing standards and protocols for hardware, software, and communication interfaces is crucial for compatibility and interoperability. Trained talent. There is a shortage of trained professionals in the quantum force, making it challenging to find the right workers. Overall expense. Quantum computing is expensive due to the challenges mentioned above, requiring substantial investments in talent, hardware, and supply chains.
Hi there, my name is Jenna, and today I'm going to be talking to you guys about the different key and industry applications that quantum computing has. Kind of what we heard earlier, quantum computing is kind of like this really big change in computation, but it also offers a lot of practical solutions to a lot of long-standing challenges in different technical sectors, and so we're going to be kind of talking about those today. So some of these key applications in which quantum computing is used in is optimization problems. So in optimization, quantum computing is really good at tackling these really intricate problems found in different sectors such as logistics, finance, and supply chain management. Normally, traditional computers struggle with how complex these different scenarios and information is, but quantum computing can explore different scenarios and explore multiple solutions simultaneously, and this provides a very efficient and optimal outcomes that wouldn't normally be found or would take way too long to find. For example, like in the logistics industry, where quantum algorithms can redefine route optimization and they can better scheduling and resource management, and leads to a lot of significant time and cost savings. In addition, there's also drug discovery and kind of in the medicine sector. Quantum computing plays a really large role in revolutionizing drug discovery. Traditional methods for simulating a lot of these molecular interactions are time consuming, but quantum computing can simulate a lot of complex chemical reactions with unheard of speed. And so this acceleration expedites the identification of potential drug candidates and also brings us closer to a lot of breakthroughs in medicine and treatments for various diseases. Additionally, it's also used in machine learning AI, and so in artificial intelligence or AI, quantum computing offers a large boost to machine learning algorithms. They can process and analyze these large databases that are given to them a lot faster than classical computers, and so this acceleration of analyzing this information data can open a lot of doors to more sophisticated AI applications, a lot more intricate. And that's kind of including with advanced data analysis, pattern recognition, decision making, etc. And then finally, for kind of one of the key applications would be cryptography and security. Quantum computing and cryptography is kind of like a two-way. On one hand, it strengthens security through advancements in creating quantum-resistant cryptographic methods. And then on the other hand, it also poses a challenge by potentially breaking the existing encryption techniques. So this dual role is both good and bad, but overall is a very good advancement as it shapes the future of secure communication, pushing us to evolve encryption methods, and as quantum computers get a lot more advanced. And so those are kind of like the key applications, and I kind of mentioned a few of the industries that quantum computing impacts, but overall it's kind of like finance, healthcare, logistics, and so overall quantum computing has a large impact on a lot of different sectors of your day-to-day life, and quickens a lot of the applications that normally take ages to complete.